Okay, good afternoon. Let's get started. Have your clickers out. And we're going to because we're going to be doing some clicking right away and throughout the lecture. So get those ready. A couple things. I updated the Did You Participate in Lectures 4 and 8, September 5th and September 19th in the gradebook page. And if you still have a 0 there, you better check in with me after class. Although most of you are good. Most of you, if you have been clicking in class, you have a 1 there. If you don't, if you're still not registered, you're not showing up, you have a 0 there. Okay. Concerning the extra credit visits to the observatory, I know students were asking me about it yesterday. The Nights Under the Stars public event schedule here. I'll give you the link for it. But what you're going to do is look down at the bottom of the page where that black arrow is, and they don't have anything going right now. So they didn't have anything yesterday, but maybe next week they will. All right. So this is these are the two web addresses. Copy down the one on the bottom. That's a bit.ly address, a little bit easier to find, to type in. And hopefully next week we'll have a session, and at least once or twice, and hopefully more, between now and December. So here's a little blurb from that page, and it kind of explains something that you need to be aware of. Florida's fickle weather means that we cannot be sure an event will occur, i.e. Nights Under the Stars, until just before the scheduled time it starts. That's a pathetic sentence. The English department would not approve. Anyways, so a lot of times they'll wait till the last minute before they cancel is what they're doing, is what they're saying there. They'll try to go if they can. Green means we're open. So when you go to that page and you look on the little schedule at the bottom, if it's green, that means ching, show up if you can. If it's red, no go. Closed due to weather. And if it's purple, that's the one where you got to just ride it and just try to see what you can see up to the last minute. And they'll make a go, no-go decision at some point before it's supposed to start. So whether that's 8:30 or 9:30 or some other time. And that'll be on that little page. So go ahead. So what we're looking for is green. When the date is written in green, that means it's good to go. And you can go up there and observe. And you'll have a lot of fun. I love going to them myself. I try to go at least once or twice per semester. Okay, clicker questions. Let's do question number 1. Remember to put in the frequency DD. So if you're using the clicker for the first time, hold the power button down until the rectangle in the display flashes. Then type D and then D again. All right. Oh, actually, we don't have a question yet. This is not a question. This is a blurb. We're going to have a clicker question. So this, you can't do anything here yet. Although I see 10 people have clicked in an answer. Good one. Oh, and I can tell who. They're all over the place. Now we got a bunch of white. All right, you guys. Everybody's a comedian. Anyways, if you weren't here Tuesday and you didn't get the handout, you can look at the PDF and print it out, for the new amended syllabus. And as always, the syllabus, in this case, the amended syllabus, is like a contract, all right? And I have to hold myself to that test schedule, whether I like it or not. Hurricanes notwithstanding, and so go ahead and get that thing. We had to do some major surgery on it, but an examodectomy. But other than that, everything else is the same. So, all right, now we'll do some clicker questions on the amended exam schedule. And hopefully it'll be as thrilling today. Can you imagine being this astronaut? Can you imagine the thrill, the adrenaline? You know, his heart must have been going about 2,000 beats a minute. No, man. Did you see anything? No, that's it. Dude, he's out there. That was 1984. He had a maneuvering jet. I believe it uses nitrogen. And they just, expel some nitrogen out the back end or in any direction, and he goes the other way. So if he wants to go forward, he expels some nitrogen out the back end. If he wants to back up, he just expels some nitrogen out the front end and so forth. But I tell you what, Bruce McCandless, what a thrill. All right, now here's something thrilling. Multiple choice question. Go ahead, you guys. Answer this one. Hopefully everybody gets it. Okay, 15 seconds. Is that my lunch? No? Yes? Maybe? Looks nice. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, most of you guys got it right. 87%. It's 3 midterms exams. That's the examodectomy. Okay, question number 2. Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, most of you got this one right. Very good, 50 points. So in addition to an examodectomy, we redistributed a few points into the midterms and the final. Another question, the amended plan. Question number 3 for today. Read carefully. Who just voted for A? See, if you vote for, I can see who you are. I can look in the data, man. I can figure out who's the Weisenheimer voting for A. Oh, somebody voted for B. I don't know. It's just sometimes you guys, I'm not getting through to you. Okay, anyways, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, it's the option E is the correct one on this. So we're dropping, because we did the examodectomy, instead of dropping the lowest and keeping the best 3, now we're dropping the lowest and keeping the best 2, because there's only 3 midterms now. All right, visual IQ test here about the dice. You notice anything? Do you notice?
Yeah, the other dice is messed up.
That's it, good. The other dice is messed up. Actually, both dice are messed up.
Other two.
there's a bunch of 5s on the one in back, and there's at least 2 2s in the one in the foreground. All right, so now why is that? Well, whoever invented those dice wants to roll 7s. All right, now I'm bringing a serious point up here. If you were on the phone with somebody and you were playing dice, you're gambling, it would become really boring because 7s would be coming up the whole time and you'd be losing your shirt, so to speak. The phone line that you were on would be considered a low information channel. So make a note, cheating dice, lots of 7s, boring, low information. Scientifically, we would say that phone line is transmitting very low information. We would also say that the source of the information coming down the line is low entropy. So the dice are a low entropy system. All right? And so that's the cheating dice. Now, a fair pair of dice are not going to be as boring. You're still going to get some 7s, but look at what you got with a fair pair of dice. Here they are. Those are all the different combos. Now, there's combinations over here on the right that I guarantee you, it's not clear because you can't really see what the cheating dice have, but I guarantee you there's some of the combinations here on the right that you can't get with those red ones, all right, because they have at least 3 5s and 2 2s on the other dice. So something's going to be missing. So make a note, fair dice, many combinations, not boring. Game on, you're going to have a little bit of fun, throwing dice, if that's your bag. Now, scientifically, you would say that it is a higher information system, simply because there's more possible combinations for a fair pair of dice. For the same reason, we would say that the dice, the fair dice, constitute a higher entropy source. All right, so there's your comparison. Cheating dice and fair dice. Cheating dice are low information and low entropy. Fair dice, higher entropy, higher information. All right, now why am I bringing that up? Well, there is a serious reason for bringing that up. This is just kind of like a little side note before we get to the meat of the lecture, and that is that this idea of entropy and information is right at the middle of the whole physics of black holes. Now, we're going to be talking about black holes toward the end of the semester. And actually, for those of you guys that have an interest in astrophysics and so forth, I'll be thinking about black holes all semester. You may not realize it, but I'm always thinking about black holes and what they mean. The colloquial definition of a black hole is an object for which the gravity is so intense that even light does not have light does not attain escape velocity. And everything has an escape velocity to get away from the Earth's gravitational field. Okay, it's pretty high, but light easily does it. You throwing a baseball, no way. But if you have a big enough rocket, yeah, you can do it. But black holes, the colloquial definition is the escape velocity is larger than the speed of light. That's how strong the gravitational field. But the real way to state the fact that you have a black hole involves entropy and information and the surfaces of the event horizon. You may have heard the word, raise your hand if you've heard that word entropy before. Okay, good. Entropy is sometimes associated with thermodynamics, and actually black hole thermodynamics is a thing that was developed about 40 years ago, so it's kind of cool. Anyways, we're aiming at understanding this diagram up here. this black hole and its companion, the orbit of its companion, S2. And so that's why we're talking about sevens and the fair dice. Okay, let's wrap up and kind of catch up to where we were yesterday or Tuesday. This is a nice little map of constellations, Sagittarius and Scorpius. And you can see the teapot during the summer. And I always think of it as the teapot pouring tea down the Milky Way. And you can see this kind of whitish streak here from upper left down towards the bottom. That's the Milky Way. And it's hard to see in Orlando, but yeah, you can definitely see the teapot for Sagittarius. Center of the galaxy is right in here. And here's Antares in the constellation Scorpius. And they don't make it red, but if you were to look at Antares, and if it's clear tonight, you could be able to see it in the south. Antares is a red star. It's definitely, it looks red to your eye. Anyways, let's keep going. We talked about these ones, Orion, and we talked about a few objects near Orion, Sirius, the constellation Taurus, kind of above Orion, and the Pleiades cluster. We talked about the Big Dipper, Ursa Major, part of Ursa Major, and the double stars in it. We talked about Cygnus the Swan, and the fact that in that constellation there is an object that we think is a black hole, a source of X-rays, very small, and just the right mass that it's so small and enough mass that we think it's a black hole. All right. Now, we stopped at this quote last time, and I want to restart here today with this. Today, and this is a quote from section 2.1, I guess. Today we use the term constellations to mean one of the 88 sectors into which we divide the sky, such as the United States is divided into 50 states. So the borders of the constellations, they look kind of like the map of Utah. So here's Utah up here. It's got some corners and stuff. And most of the constellations are not rectangles, but they have some corners in it and stuff. And you can see that over here with Cygnus. This corner looks like Utah and whatnot. And so we've tiled the entire celestial sphere into 88 regions. Here's another one. This is the Andromeda constellation. And so it's kind of a weird looking shape, but yeah, that's it. We use that to identify things. Now, what's this thing here in the middle, the kind of reddish oval? Well, what that is, that's called M31. And M31, right there, that is the Great Spiral Nebula in Andromeda. All right? And so when we say that it's the Andromeda Galaxy, we mean that this galaxy can be seen. It's not in our galaxy. It's a whole other galaxy. Okay? But when we look through the constellation Andromeda, we can see that galaxy. All right? And just as a side note, in the Andromeda Galaxy, depending on how you measure it from edge to edge, the long way, it's kind of tilted with respect to us. It's actually circular. It's like a disc with spiral arms and so forth. It's about 3.3 degrees. It's larger than the full moon. Now, you can't see it with your naked eye. You can't see all those spiral arms. But you can see this nucleus with your naked eye. If you know, it's tough to see, but I've seen it on a clear night in the constellation Andromeda. And so let's keep going. Now I'm going to talk about Copernicus, Tycho Brahe, and Johannes Kepler today. And we're now in chapter 2.4. Let's talk about Copernicus for a little bit. Copernicus made a breakthrough with the heliocentric model And many scholars and philosophers and scientists consider his work as achieving a scientific revolution, the Copernican revolution. All right? Now, he was an interesting guy. He was a priest, a Catholic priest in Poland, faithful Poland, and also a medical doctor. And in those days, the 1500s, a lot of guys were learned in many of the sciences. So there weren't, it's not unusual to read about people in England and Poland and France, Germany, different places of that kind, who were simultaneously, like Copernicus, he was a priest, he was a doctor, and of course he was a mathematician and a scientist. Another famous character from about the same time is Thomas More in England. St. Thomas More, the man for all seasons, a famous movie made about him. And he was a friend of King Henry VIII, so 1500s now, the century before Shakespeare. And I was reading a biography of Thomas More, and it mentioned the fact that he was a lawyer. And he was I think it was kind of like a judge, and then he became promoted to either the chancellor of the exchequer or some kind of an attorney general or something like that in England. I can't remember the exact, but he was a big, he was in King Henry VIII's cabinet, you might say. He was one of the ministers. And but he was an attorney. He was famous as a very fair and honest attorney and everything. But I read his biography and I didn't realize it. He was actually a tutor to King Henry VIII in astronomy and mathematics. And so that would be like a Supreme Court justice or the Attorney General here in the United States who also has a PhD in astrophysics and a PhD in mathematics, as well as a doctorate in law. So, and that would be very, very unusual in our day, but back in those days it wasn't. His book, the one book that changed it all for everybody, according to some philosophers, De Revolutionibus Orbium Celestium, on the revolution of the celestial orbs or the celestial spheres. In other words, he was talking about the heliocentric model. And what he was able to do was work out the periods. They knew the periods of the planets, of course, fairly well. And he was able to work out the relative distances of each of the orbits from the sun. And how did he do it? He based everything on the astronomical unit, the AU. Now, we've talked about that already. And in this day, they didn't know the distance to the sun in light seconds, about 500, we now know, or miles, 93 million miles, we now know, or kilometers, 150 million kilometers. They didn't have radar range finding. They didn't have, triangulate. They didn't triangulate the distance, but they could work out in terms of similar triangles and stuff with the astronomical units. Now, here's an interesting quote, a pull quote from section 2.4. His ideas, although not widely accepted until more than a century after his death, in other words, even after Galileo, his ideas were much discussed among scholars at the time and ultimately had a profound influence on the course of world history. And that is indisputable. The Copernican system, the heliocentric system, ran counter to the geocentric system that was championed by the ancient Greeks. A bunch of the ancient Greeks figured that, the sun is the center and everything's orbiting the sun. And then another bunch of the ancient Greeks thought, no, it's the earth at the center and everything orbits the sun. And so the geocentric faction won out. Plato and Aristotle and those guys won out, and that carried for over 1,000 years into the time of Copernicus. But once he published his Revolutionibus, things started to change. And here's another quote. Copernicus could not prove that the earth revolves around the sun. Matter of fact, with some adjustments, the old Ptolemaic system of the ancient Greeks, the geocentric system, could have accounted as well for the motions of the planets in the sky. But Copernicus pointed out that the Ptolemaic cosmology was clumsy. So emphasize the word clumsy. And it lacked beauty and symmetry. So emphasize the words beauty and symmetry. It lacked beauty and symmetry of the successor, the heliocentric system. So Copernicus could not, and the basic reason he couldn't is because he didn't have telescopes. They could have made telescopes in his day, but they didn't until about 100 years later. About 1609 is when Galileo started using telescopes to observe the stars and the planets and stuff. But what's interesting about this is that this term symmetry. Now, we have a mathematical and physical theory for symmetry. You know, like the human body has left-right symmetry, bilateral symmetry, we call it. The math department would call it. They give it a what they call a symmetry group, or they might call it a reflection symmetry for the human body and many organisms and stuff. Now we have a mathematical basis for handling that, and it's actually very powerful. So just saying that something is symmetry, it sounds nice, but actually it has physical meaning. If you see a physical system that displays symmetry, there's a physical reason involving forces and accelerations and momentum and kinetic energy and all that stuff. There's a reason for it. Now, we haven't been able to figure out beauty. Maybe we will. By the time you guys are old and gray, and you're thinking, yeah, back when I was your age in Dr. B's class, he said this day would come, and no. Maybe. But yeah, symmetry, definitely, we have a handle on it. And the Ptolemaic system, and yes, I'm pronouncing the silent P in Ptolemaic. The Ptolemaic system, named after the Greek mathematician, he lived in Egypt, Upper Egypt. Or no, I should say, he lived in the Nile Delta of Egypt. Ptolemy, he was able to render the most detailed version of this system. And it's kind of an interesting fact that it lasted 2,000 years probably. Even in 1636 in Harvard, they were still using the geocentric system of Ptolemy. And Galileo learned it when he was in school, a little bit before 1636 at Harvard. All right, now I'm going to take a break, and I'll be back in just a second. Let me pause the podcast. I have to adjuster coming to look at my roof. So after the storm. Okay. All right, let's talk about Tycho Brahe. Tycho Brahe, come on. Okay. Tycho Brahe was an astronomer in Denmark that he came after Copernicus, and he made a specialty of making what? What about the podcast?
Unpause it. You gotta start it again. You paused it. Unpause it. Yeah.
It's going. Why? I'm not really sure. Why would you say that? Yeah, and I got it going again. It's recording.
But he was just reminding.
Yeah.
All right. Okay. So his specialty was making very careful observations. He did not completely savvy the system the way that, as a matter of fact, Copernicus and Kepler after him were able to. But he was famous for making huge improvements and refinements in the measuring of stellar positions. Now, he was naked eye, so he couldn't magnify or intensify the light of a star. And so he couldn't see any more than any naked eye observer, but he could locate it very, very carefully. Okay, and so he was interested in the same thing that we are interested in this day, and that is using the Hubble Space Telescope for a fantastic machine. The Hipparcos spacecraft, another fantastic machine that is designed to see better, see further. And the Hipparcos is not, they're not after galaxies and distant galaxies the way the Hubble is. The Hipparcos is ultra precise for measuring the positions and the variations of positions of stars, and by that triangulating the exact distance to a star fairly close to our solar system. Another factor that I want to mention to you is that in those days, they could make statements. They couldn't distinguish adequately experimentally. But the key is, after you've made your record of observation, you want to then be able to come up with some theory and make a prediction. And if you can make a prediction, then you'll be able to distinguish between the competing ideas. In this case, the geocentric system and the heliocentric system. And actually, let me just go back here and make a note here that this is now, we're dipping forward into 3.1, and we're going to dip backwards into 2.4 on Tuesday to talk about Galileo a little bit more. But let's keep going, talking about Tycho Brahe and those guys. Now, here's the observation that they would like to have made but could not. And what they would like to have been able to see are the phases of Venus. This is figure 3. And from Earth, you can see, let me move my cursor over here. Let's see. Come on, cursor. Okay, here's you on Earth, and under the right conditions, it's possible to see, when you're looking at Venus, the morning star, or Venus, the evening star, to see a crescent phase. Now, they couldn't do it in the day of Tycho Brahe because you need a telescope, and even a good pair of binoculars will see it. Half phase, instead of a half moon, a half Venus. And that's another one. With the naked eye, I don't care how sharp your eyesight is, you can't make that out. Gibbous phase, that's past half but not full. And of course, back here is full, but you wouldn't be able to see that because it's on the other side of the sun. Okay? So all these different phases, those guys, if they could have seen that, it would have locked in the heliocentric system. This is heliocentric. This is basically a prediction of the heliocentric theory. They couldn't see it until the day of Galileo, and we'll talk about Galileo on Tuesday. But here's an interesting note. You know, Tycho Brahe got in trouble, I guess, with the King of Denmark, and he had to skedaddle and head out to Prague in Bohemia, and there was another king over there that hired him as the court astronomer. And one of his assistants that he hired, excellent personnel move, was Johannes Kepler. In the year before his death, Brahe found a most able young mathematician, Johannes Kepler, to assist him in analyzing his extensive planetary data. So let's talk about Kepler. There's a picture of him there. Kind of a fancy-looking guy. Kepler was able to digest enormous amounts of data. Now, he didn't have spreadsheets and printouts and stuff. He didn't have computers like what we have. So for him, the records of Tycho Brahe were maybe bound into a big, thick book, you know, as big as one of those big Bibles in a church, except that all the pages are bunches of numbers, you know, numbers about Venus, and then another 100 pages later, numbers about Mars, and then another 100 pages, numbers about, you know, the time and position of Saturn and Jupiter and so forth. All right? And what he saw in the data was also a profound change to the ideas about what the universe was doing. You know, Galileo famously said, Mother Nature is like a book, a grand book, and its language is written in mathematical language. And if you understand the geometric language of triangles and circles and other geometric figures, you can figure out what Mother Nature is doing. And so, but nobody had thought the planets moved on ellipses, but that's what Kepler was able to see. Now, go ahead and make a note of this, 5C. Unfortunately, page 63, that's a reference to the old physics, the old astronomy textbook, but it's still good. Kepler's key discovery was that planetary orbits are not circles, but instead are a special type of oval called an ellipse. Now, we're going to talk about that special shape, the ellipse. We're going to do some clicker questions, and we're going to calculate. All right? And this is the facts of life astronomically. You know, this picture up here is an ellipse, and it's fairly oblong. It's a lot wider than it is tall. Okay? Now, comets take those shaped orbits, but most of the planets, go ahead and make a note of this, most of the planets technically are ellipses, but they're very, very close to a true circle. And a true circle is just a specialized version, highly symmetric version of an ellipse. And most of the planets, but, you know, Kepler, here's a famous quote from Kepler. You know, he's looking at Mars, and he said, if I had believed that we could ignore these 8 minutes of arc, that's a very small fraction of a degree, I would have patched up my hypothesis accordingly. But since it is not permissible to ignore, those 8 minutes pointed the road to a complete reformation in astronomy. Okay? So he's working on these ellipses, and, you know, in Hollywood, you know, you could ignore what the numbers say, and you're writing some science fiction movie with scary monsters that can hypnotize you from, you know, outer space and all that kind of stuff. But a scientist, a real scientist, they have to let the numbers do the talking, or in this case, the measurement numbers. Okay, and he said, I cannot ignore those. He was trying to fit the orbit of Mars to a circle and could not do it. Now, most of us, if we looked at the data and plotted it out on ultra careful graph paper, we would be able to say, boy, that looks like a circle to me. And if you looked at the orbit of Mars, in fact, the textbook says, if you look at the orbit of Mars carefully, it's very hard to distinguish from a perfect circle. But Kepler distinguished it. All right. Now, let's take a side note about angles, just to give you a little bit of nomenclature. Okay, angles, degrees, minutes, and seconds. We've already talked about this a little bit. A full circle is divided up into 360 degrees of rotation. And this traces back to the ancient Sumerians who based their counting system on 612 and 60. For some reason, I've never read why they did that, if anybody knows. Now, 1 full degree is further subdivided into 60 minutes of arc. Okay? And so a 60th of a degree. So think of a degree on a protractor and then divide that into 60 equal slivers of rotation, and that's a minute. 60 minutes of arc. Now, the full moon is 30 minutes of arc, about half a degree. All right? Your vision can resolve things 1 minute of arc apart. So, but if you wear glasses, you might notice that you can't see things as clearly. Things look a little bit more blurry. And then if you put your glasses on, it corrects your vision, and you can see with a resolution of about this level. Now, 1 minute of arc can be traditionally subdivided further into 60 arc seconds. And so an arc second is a 60th of a 60th of a 360th of a full circle. So an arc second is a teeny fraction of a sliver of a degree. Now, item number 4, it's not in the slide, but let me give you item number 4. The aiming accuracy of modern telescopes would have really thrilled Tycho Brahe and his comrades, because a modern telescope can resolve angles on the order of a millisecond of arc. Okay, so a degree, a minute, a second, and then 1,000th of a second. So Hubble can aim itself, within a few thousandths of a second of where it wants to go. And all modern telescopes, the really good ones, like the ones up on top of, there's big fancy ones on top of the volcanoes in Hawaii and bunch down in South America and stuff, down in Arizona. You have some good ones. And so the milli-arc seconds is definitely a unit that that astronomers work with now. All right, so let's talk about Kepler's 3 laws of planetary motion. This is from section 3.1 now. Okay, here's a quote. Kepler found that Mars has an elliptical orbit with the sun at one focus. The other's focus is empty. All right, now let's put together an ellipse. Go ahead and sketch in your notes an ellipse of about this shape. So just kind of eyeball it. I made mine a certain set of dimensions, and I'm about to give them to you, but just make yours wider than it is tall. Okay? Just like my yellow with a red edge. Okay? Now the major axis is the horizontal axis in this diagram from side to side. It's the long axis. That's why we call it the major axis. And it's traditionally divided up in half into a symbol called the semi-major axis, for which the symbol is A. So the length of the full major axis is 2A. Right? And Kepler's laws of motion are related to the semi-major axis. The minor axis is perpendicular to that. So that's the one that in this diagram goes vertically. The symmetries are left and right. Switch it left to right, and you get the same ellipse. Flip-flop it top to bottom, and you get the same ellipse. Right? So the minor axis doesn't enter directly into his laws of motion, but it would be symbolized by the letter B, the semi-minor axis. Right? So the minor axis all the way from top to bottom is 2B. All right, now in my sketch here, I made my semi-major axis 300 pixels. So the total width is 600. Okay, the total major axis is 600 pixels. And my semi-minor axis I made to be 200 pixels. All right, now you might not have that, but if you jot it down, you can actually do it in PowerPoint if you want, later on, and you'll get a shape that looks just like that. Now, note number one, the quote says that the sun is at one focus and the other focus is empty. Every ellipse has two focus points, all right? It also has a center. Now, the center of the ellipse is where the two axes intersect. Okay, that's the dead center. The focus points are off to the left and right. So go ahead and park focus number one about here. Just kind of eyeball it in. I measured it very carefully. All right? And then symmetrically put another focus, F2, over here. Now what Kepler was saying is that the planets seem to travel along the elliptical path, the red part of this diagram. And the sun is not at the center of the ellipse. It's actually at the focus. All right, so I chose that to be this focus. All right, now, comment about this diagram. You can put this over to the side somewhere. This ellipse is very eccentric. Okay, it's a lot wider than it is tall. The planets are not nearly like this. But you know what does have an orbit like this? Comets and many asteroids. Okay, so make a note. Comets typically have elliptical orbits like this. All right? And so a comet will come around and pass near the sun right about here, and then it'll loop back around, and then it'll reach its point of furthest distance from the sun out here. And then it'll loop back around, all under the force of gravity, all right, which Sir Isaac Newton proved about 100 years after this. No, I should say about 50 years after this. Okay, so the rule for constructing an ellipse is simply this, that the distance from F1 to any point on the ellipse, like right here where my cursor is, and then back to F2, they have to add up to the same number, a constant. And that constant is actually the length of the major axis, 2a. Right, now here's an example. Here's one distance, here's the other distance. Those two dashed lines add up to 600 pixels. All right? They add up to the overall width, the full length of the major axis, 2a. All right? Now, I'm going to show you, I think, on Tuesday, how to actually do this on a chalkboard or actually in a notebook using a bit of string and some pencils and some tacks and stuff like that. All right? It's based on this diagram. And you may have seen it in high school. So that distance, the distance that I mentioned in 2D is 600 pixels. All right, another property of an ellipse is its eccentricity. Now this one, for a semi-major axis of 300 and a semi-minor axis of 200, the eccentricity is 0.745. Now go ahead and write that number in. I'm going to give you the formula for it. It's a fairly cinchy formula, and we're going to do some clicky questions with that in just a minute. The circumference and the area are all related to the semi-major and the semi-minor axis. The circumference is tricky. The area is cinchy. But yeah, you can compute both. Just like for a circle, pi r squared, that's the area. And for the circumference, 2 pi r for the circumference of a circle. And the circumference is tricky, but the area is almost as simple as for a circle. All right. Now, these points for orbital dynamics, this point of closest approach has a special name. It's called the perihelion. Okay, and that's this point right here. That para means above or adjacent. You know, periscope, you're looking above. Perihelion means the point right above the sun or right close to the sun, the point of closest approach for this comet to the sun. Now, similarly, there's a fancy name for the point out here to the right where it's just kind of poking along, and that's called aphelion. Aphelion. Helion for Helios, sun, and ap or apo meaning away. Just like the word apostle means somebody that's sent away for a specific task. Okay, same thing here. Aphelion is away from the sun, the furthest point. Now, if you're talking about Earth orbit for a satellite, some kind of a spacecraft, you'll sometimes hear, you know, those guys at Houston, Mission Control, they'll talk about apogee. G-E-E meaning G for Earth, geo. And they'll talk about perigee. Okay? And, you know, so there's various terminologies. So aphelion and apogee, perihelion and perigee are things that you frequently hear in all of this. And just last mention of the symmetries left and right and up and down, which I already mentioned. All right, now I have a clicker question for you. And this, so turn your clickers back on. And let me get to your next. And this first one's, I want you to think about it really carefully. Previous ellipse had eccentricity 0.745. What would you guess is the eccentricity of a perfect circle? That one just to the left of it is a perfect circle. This one up here, this is the one with 0.745. So what would you think is the eccentricity of this baby? Go ahead and vote. Think, and read carefully, and vote. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Let's see what you guys voted for. Ooh, let me show you this. Okay. Here's the, this must be, here it is. Yeah, so a lot of you voted for A and B, one person C, a few people, no, 11 people voted for C, 33 voted for D. So let's take a look at what the actual answer is and see if you guys can see why that's the case. The circle has no eccentricity, so B is the actual correct answer on that one. And you guys, when we're going through questions like this, it's a good study technique to jot down the question and your answer. And if you get it wrong, jot down the correct answer as well, okay? And then you can use it for studying. Now, here's the formula for the eccentricity of an ellipse. And if you think about it, for a circle is completely symmetric left. It has the same height as it has width. The major axis and the major axis and the minor axis are just diameters, and all the diameters are the same if it's a circle. So A and B in this formula for the first ellipse are two different numbers, but for a circle, they're the same. And for that reason, B squared over A squared is equal to 1. 1 minus 1 is 0. All right, so the square root of 0 is 0. And that is why we say that the eccentricity of a circle, it has no eccentricity. There's no, oblongness to it. So this formula here, the eccentricity, it's a numeric way of rating how oblong it is. And if it's a circle, you have 0 oblongness. All right? So jot down this formula. We'll use that for the next question. And let's see how it goes. All right. Now, I'm going to give you a comet that has a semi-major axis and a semi-minor axis. And I want you to consult with your neighbor, okay? And just talk it over when you're making this calculate. Use this formula. And, just kibitz with your neighbor. And you can't do it on exams, but you can do it in class, in regular lecture. And hopefully, you'll be able to figure out the right answer here. So here we go. Semi-major axis of 5, semi-minor axis of 3. So if we were using astronomical units, that would be a possible comet. I'm sure there's comets and asteroids in the solar system with dimensions close to that. It's a fairly big one, but okay, so A is equal to 5, B is equal to 3. Go ahead and calculate the eccentricity. Oh, sorry. Let me start the question. Sorry. Okay, now you can start typing your answers. Yeah, just take a minute and consult with your neighbor. And if you don't have a calculator with you today, you can still get this answer if you do a little bit of thinking. And I'll show you how to get the answer in just a second. Give you another minute. $20. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys did. Very good. Most everybody got it. C is the correct answer. A few of you did not get it, but everybody, go ahead and jot this down. Here's how you hack it. You put a 3 in here in this upper equation block, a 5 down here in the denominator, and you got to square both of them. All right. So this next move over here, top equation block on the right, 3 squared is now a 9 over here. 5 squared is a 25. But now you got a 1 over here, so you got to convert that, or you can convert that into common denominators. If you're doing this on a calculator, it's cinch you. You just do the numbers and stuff, and then hit the square root key. But if you don't have a calculator with a square root, you just kind of do it this way. Here's your common denominators. 1 is equal to 25 over 25, and then 25 minus 9 is 16. All right, and actually, you guys. The square root of 16 is 4, right? And the square root of 25 is 5. So this square root is equal to 4 over 5. So if you know your square roots, if you do some common denominators, and you know your simple square roots, 16 and 25, you can get 0.8, because 4 over 5 is the same as 0.8. Right, so there's your answer on this one. All right. Now, let me just remind you that I've been laughing ever since I left the room with the microphone on. Yeah, I figured out as soon as I came in. So I'm up here laughing. Laughing my ass off. Figuratively speaking. Anyways, so what you want to do is on memorable moments of teaching. Anyway, what you want to be is when exam X comes along, maybe you want to make sure you know how to do this. Just in the event you see something like this. Hint, hint. All right. Now, we're going to dismiss. I'll have some more homework for you, and we'll start talking about binary stars and the rest of Kepler's laws of motion on Tuesday. You're dismissed. Man, that's... I don't know. Stuff happens.
I'm not totally sure. When I enter an answer with my clicker, should a message pop up that says like it went in or
a check mark? If you want to check your clicker, come on up front. We have a few minutes.
Okay. Yeah, the check mark.
Yeah. Again? All right, hold on.
Also,
let me get this stuff. You should get, if you're communicating, you'll get a check mark.
Right.
But if you, the thing about it is, oh my God, I put that on the podcast too. So now it's immortalized, and I'm not publishing this YouTube. Sorry.
Can you pause the podcast?
Yeah, I can do it. Let me just see if I can get this. Where's my cursor? Come on. There we go.